Right, recording is rolling. So, welcome to another Monday, another week. Let me update so fast. Okay, we're back. All right, so here's what we got going on for the about next week or so. You guys know we're getting really close to this Christmas break. Oh, I want to mention too, my grade book is back and working, so I've got a week of grades to put in, so I'm working on that. But it is at least back, so that's a massive improvement. Today, main focus is going to be AP Classroom. Now, I've already had some students tell me that they were not able to access this over the weekend because I think what happens is that like pretty much everybody in the country is like on AP Classroom on Saturday and Sunday, and so it like overloads the site. So after school today, I'm going to go back and reopen that for a few students who were trying to get on it that weren't able to actually access. Right, so we'll go over the questions today. Next couple of days, I have a rotational inertia lab for you guys. You guys see back on that lab table, there's some PVC pipe in a T shape. That can rotate about that central vertical axis. And I'm going to have you guys calculate what the rotational inertia associated with that is. I'll show you guys how to do that. Have you guys make some measurements, do some calculations. I'm going to have you guys do a graph. I'll also have you guys do a full AP style write-up, which I do on select labs if I think it'll be helpful for you guys. And I think tomorrow would be a good place to do that. So I also, over the weekend, created a grading rubric for it that's pretty similar to AP, so that's what we're doing the next couple days. Then by this Thursday, I'm going to get into the midterm review in earnest, and I've already given you guys this review page full of questions that part of the midterm is going to be conceptual questions like these. But while I'm going over those questions, I'll also go over some common classic questions, do some graphs, like a full comprehensive review. Now, there are some other review pages that I did post to Google Classroom, like the first few that I gave you guys, like very first day of school. Like for example, here's one of them here. I got a page full of variables on it. There's AP equation bank. You guys remember that? There's this review page. Those are available on Classroom, or you might have them in your folder from the very first day of school. Kept good track of those. Do you guys remember this coming Friday? Your Chapter 8 homework puzzles are due. We have gone over all the main assigned ones already as of last Friday. So if you want to turn those in early, some students already have. If you want to get those off your hands. And then your guys' rotational dynamics quiz, which I did get to you guys by the end of last week. This is due exactly 1 week from now. I mean, these are the due dates I set, so I'll go ahead and just stand by those. So you guys got plenty of time to do these also. Okay. Right, let's take a quick look at this. I got omega versus time graph. Oh, and look at how omega, that's angular velocity in radians per second. Notice how that's decreasing. I can show you guys pretty well exactly what that would be. Turntable, give it a spin. It's going some radians per second, but hey, notice how it's slowing down. And after some time interval, it comes to a full stop. Now, if you assume that the rate that it was slowing down was uniform, then it would create a graph that's exactly this shape. Now, one thing that you should be able to get out of a physics class like this is say, like, what all kinds of information could you extract from a graph like this? Obviously, you can know how fast it's spinning at any particular moment. But also, how about this question? How far did it spin during that time interval? How could you figure that out? Or does anybody know the answer? How far did it spin? How many radians? 90 radians, exactly. How'd you know that?
Area under the curve.
It is area under the curve. Okay. Now, if you forgot why, or how about a general principle to figure out why? Look at the variables on these axes. I got radians per second and seconds. Hey, what happens when you take radians per second and multiply by seconds? What does that give you?
Radians.
That does give you radians, which is what we're interested in. How far does it turn? That's a huge hint that it might have something to do with area. Right? In fact, how this is taught in calculus, I know about half you guys are in calculus, is normally what you do is start by splitting this up into a bunch of tall, skinny rectangles, right? Be like distance is speed times time. Of course, this is angular, but same principle, right? Speed times time, speed times time, speed times time, right? Add it all up, right? So yeah, it just turns into this triangle at 1/2 base height. So 6 seconds times 30 radians per second divided by 2, that is 90 radians. How many revolutions is that? 90 radians. I'd have to divide by what? 2 pi, because they're 2 pi radians per revolution. That's about 14.3 revolutions. So it says thing spun around like 14 times. Right? Hey, what else could you extract from this graph? How about the rate that it was slowing down? Alpha, radians per second squared. That's angular acceleration. What property of the graph is that? That's the slope, rise over run, right? Rise over run. That's the change in radians per second per passing second. That's radians per second squared. Right? And what is the slope of that line? -5 radians per second squared. So it's losing 5 radians per second every passing second, right? Okay. Right. All right, time to flip over to AP Classroom.